Welcome. Today we're presenting a slide about atomistic and crystalline structures for silver, palladium, and indium nitride, presented by Ryan, Dustin, and Laurent himself. To start off, silver has a face-centered cubic crystal structure. This is a cubic closed packed structure, as you can see on the board. Palladium also has a face-centered cubic crystal structure, and it is also a cubic closed packed structure, again on the board. Starting with silver, silver has a coordination number that's equal to 12, and so does palladium. Palladium coordination number is the number of closest neighbors. As for atomic packing factor and theoretical density, atomic packing factor for silver is 74%, as well for palladium. However, for silver, theoretical density is 10.61 grams, and theoretical density is 12.15 grams. To further explain the math, here is Ryan presenting the work for it.
Hello, I'm Ryan, and I'm going to be explaining how to find the atomic packing factor. So our equation for the atomic packing factor is equal to the number of atoms times the volume over the volume of the unit cell. So in an FCC structure, in order to find the number of atoms, it is going to be 6 times 1/2 plus 8 times 1/8, which is going to be equal to 4 atoms in a unit cell. And in order to find the volume of the unit cell, we have to take the front face of the cell, and the edge length of a unit cell is equal to A. And we have to find a relationship between A and R, the radius of the atoms. So we take the diagonal, which using Pythagorean theorem is equal to the square root of 2A, which in SCC structure, this diagonal has 4 radiuses. So you can set radical 2A equal to 4R. And then R over A is equal to radical 2 over 4. And also the volume of an atom is equal to 4/3 pi r cubed because it's a sphere. So now we can plug in some numbers here. 4 times 4/3 pi r cubed. Be over A cubed, which is the volume of a unit cell. And now we need to get that A cubed into terms of R. And in order to do that, you just plug in radical 2 over 4. So in total, we're going to end up with 16 over 3 pi times radical 2 over 4 cubed. And when you multiply this by 100%, you get 74%. And this is going to be the same for silver and palladium, as they are both FCC structures. Alright, so now I'm going to explain how to find the theoretical density. I've already listed some values that we're going to need for this equation. So we can start with the regular density equation, P equals m over v. For the mass in a FCC unit cell, there are 4 atoms. So we can say that the mass is equal to 4 times the molar mass. In order to get grams, we divide the molar mass by Avogadro's number, which I have listed right here. And so that'll be our mass. And then for the volume of a unit cell is equal to A cubed. And from our previous example, we found that R over A is equal to radical 2 over 4. So using this equality, if we plug it into our volume, we get R cubed. Now we have our volume and our mass, so we just plug it into the formula over here. And so for silver, we would plug in these 2 numbers here, which is the molar mass and the radius. And our density for silver is equal to 10.61 grams per centimeter cubed. And for palladium, we plug in these 2 values here, and we get our density of palladium is equal to 12.15 grams per centimeter cubed.
Our semiconductor is indium nitride. Indium nitride has a hexagonal closed pack crystal structure. Like FCC, this is also a cubic closed pack structure. And because it is also a cubic closed pack structure, it also has a coordination number of 12 and an atomic packing factor of 74%. Should I introduce you?
No. I'm Dustin, and I'm going to show you the crystalline direction family and the plane family in an FCC structure. So in this graph, we have the vector direction of 1, 2, 0 shown on the graph, and this is the direction family. And here we have the 1, 1, 1 family, and this creates a plane, and it's a triangular plane. Okay, now we're gonna try and find the linear density in the 1, 2, 0 direction for silver and palladium. So first you'll start with the direction shown in these squares, and the letter A represents the length of the unit cell. So now we'll use the Pythagorean theorem. So c squared equals 2a squared plus a squared. And when you solve this for c, you will get c equals the square root of 5 times a. And you can correlate this to the radius of the atom, and that a is equal to 2 times the square root of 2 times the radius. And now the equation for linear density is the number of atoms all divided by the length. And we can substitute now. So for this problem, we have 1 atom divided by the length, which is the square root of 5 times a. And now we can substitute for a. So now we get 1 divided by the square root of 5, or 1 divided by the square root of 10 times 2r. And so now using this equation, we can plug in for R. So for silver is 0.144 nanometers, and for palladium is 0.137 nanometers. And after you plug in and solve for silver, you'll get 1.10 nanometers to the -1, and for palladium, you'll get 1.15 nanometers to the -1.